Hello everybody, this is Dr. Christopher White and welcome back for part 2 of our video looking at the lab exercise, plate tectonics and rates of motion. So we've moved on to part 2 of the lab exercise, and in this part we're going to look at hotspots, how we use them to infer plate motion and how we use them to calculate the rate of plate motion. So if you've watched the plate tectonics lecture, hopefully you remember that hotspots represent bodies of superheated mantle rocks which rise from the core mantle boundary up through the mantle. And that's primarily due to them being so hot, and obviously that gives them buoyancy. So these bodies of mantle rock are rising up through the mantle and eventually they get stuck beneath the lithosphere. Now, as the mantle rock is rising, a couple of things are going to happen. Number one, it's very, very hot. So that's going to encourage the mantle rocks to begin to melt. Another thing that's going to happen is that as the mantle rocks are rising, they are also going to experience lower and lower pressures. This too is also going to encourage the mantle rocks to melt. And so when the mantle plume gets stuck underneath the lithosphere, you have a lower pressure environment combined with very, very hot rocks. And so the mantle plume is going to melt, producing a mafic magma. Now, when this mafic magma is trapped under oceanic lithosphere, what's it going to do? Well, it's going to melt, partially melt, should I say, the oceanic crust, and that's going to not have a substantial effect on the composition of the magma. So you're going to still have a mafic magma that's going to rise to the surface where it's going to be erupted. And this is the type of magma that we find in oceanic island chains such as the Hawaiian Islands or the Galapagos Islands. Now, if our mantle plume gets stuck underneath continental crust, the situation is slightly different. Once again, our mantle plume is going to melt, producing mafic magma. However, this very hot mafic magma is going to find itself in contact with continental crust. And continental crust has a composition of somewhere between felsic and intermediate. So when that continental crust starts melting, it's going to produce felsic or intermediate magmas. Now, these felsic and intermediate magmas will mix with the mafic magma from the mantle plume, and this is going to produce a magma with an approximate composition of intermediate. This will rise to the surface, where it will be erupted and it will form the rock andesite. So when we look at these two different settings associated with hotspots, we tend to find that with these oceanic island chains, it's basalt that's being erupted, and with the continental hotspot occurrences, we're going to see mostly andesites being erupted. So arguably the primary example of a continental hotspot is the Yellowstone hotspot and the Yellowstone caldera that it produces. So a caldera essentially represents an area of the continental crust that has dropped relative to the surrounding topography. So if we look at figure 3.5, we can actually see that there are several of these calderas that have formed as a result of the Yellowstone hotspot. So up here we have the current Yellowstone caldera, where volcanic activity is still ongoing. And as we move towards the southwest, you can see we have several older calderas. These are volcanically inactive. There's no longer any volcanism going on. So the formation of a caldera is caused by a magma chamber emptying. So as we just mentioned, there's going to be a lot of magma produced by the presence of this hotspot, and that magma is going to rise into the crust where it's going to form a magma chamber. And this magma chamber is going to keep filling up with magma until it eventually reaches a point where that magma can now exit the chamber and be erupted onto the surface. And that's exactly what happens. So the magma exits, rises up through conduits, is erupted via volcanoes, and what happens is the rate at which magma leaves the magma chamber is faster, is higher than the rate at which it is replenished. And so the magma chamber begins to empty. And so as the magma chamber begins to empty, you end up with a void. And so the weight of the overlying rock above the magma chamber starts to cause that rock to drop down into the magma chamber to fill the void that's created. And so this means at the surface, the crust is going to start dropping into the magma chamber, and that's going to produce one of these features which we refer to as a caldera. And Over time, these calderas will naturally form topographic lows. They will, however, be volcanically active, and so there will be plenty of andesitic and felsic volcanoes. Within the caldera itself, there will be erupting intermediate and felsic lavas, so producing andesites and rhyolites. And so each of these calderas is a topographic low which is full of intermediate and felsic volcanic rocks. Now, as we move away from our hotspot, why do we see these calderas getting older? So as we move towards the bottom left of our diagram, we can see the age of each caldera is increasing. And that's simply because when a caldera forms, it's going to be formed in response to a burst of volcanic activity. Obviously, that volcanic activity will eventually cease, and the plate motion will then carry that caldera away from the hotspot. And as the caldera begins to move away from the hotspot, a couple of things will happen. Number one, it gets taken away from its source of magma. So this means that your caldera will then become volcanically inactive. So the volcanoes will stop erupting. Another thing that will happen is that your caldera will also start to subside even more. And the reason for this is the magma that's under the caldera, the hot mantle as well, will naturally cause the topography in that area to rise up once again because of the buoyancy of that magma. However, once that magma is removed, the caldera is naturally going to start subsiding. So it's going to start sinking a little bit because the hot, buoyant magma is no longer there. Now, this is the same thing that we see happen with the Hawaiian Islands. So the current volcanically active island of Hawaii represents the location of most modern eruptions taking place in Hawaii. Now, eventually, plate motion is going to carry the island of Hawaii away from the mantle plume, away from the hotspot. And when this happens, number one, the volcanoes on Hawaii are going to become inactive because they've been removed from their source of magma. But you're also going to see the island of Hawaii begin to sink. It's going to begin to subside because all of that buoyant, warm magma is now being removed. And so the island's going to naturally start dropping. And so that's why when you look at the Hawaiian Islands, if you actually look at the complete chain going off towards the northwest, you will actually see that only a few of the islands are above sea level, with the majority of them actually below sea level. And that's simply because as the magma underneath the islands gets removed, the islands naturally drop, and eventually that drop takes them below sea level. Okay, so what else do we need to know about hotspots? Well, another thing we need to know about hotspots is that they are stationary. The hotspot itself does not move. What does move are the plates going across the hotspot. So as we can see, here's our selection of calderas related to the Yellowstone hotspot. We know the Yellowstone hotspot is currently located right here because this is the modern caldera, which is currently volcanically active. And then as we move away towards the bottom left of the diagram, we can see the age of the calderas increasing. So we know that the direction of plate motion is essentially in the direction of the calderas getting older. So there's a hint for question 1. So how can we use this? Well, for each of the calderas, you can see we have locations where we have an age of the volcanic rocks from each of these calderas. In fact, we actually have 2 from the modern caldera. And so we can actually use this information to calculate rates of motion. Okay, so we're going to drop down to question 1. So question 1 is simply, what's the trend of the caldera chain? So the trend essentially is what direction is the chain aligned? So is it aligned east-west, north-south, northwest-southeast? So please, from the 4 options, select the one that you think best fits the diagram, figure 3.5. Now, using the ages for the calderas, so we can see the ages are marked out here for each of these white circles. So using the ages of the calderas in figure 3.5, give a compass direction, so north or west, northeast, southeast, for the direction of plate motion. And remember, the direction of plate motion will be in the direction of the rocks becoming older, okay? Because those rocks are being taken from the hotspot and they are being transported away from it. Okay, so for question 3, we are once again going to be using figure 3.5, and we are going to use figure 3.5 to calculate the rate of plate motion. Now, in this case, what we're doing is we're actually calculating the rate of plate motion between each of the different locations for which we have an age. So we're going to calculate the distance from here to here in centimeters. So the distance between C3 and C1, we're going to calculate the distance from C1 to this point here, from this point here to this point here. So we're going to get those distances in centimeters, we're going to get the difference in age between the points, and we're going to use that to calculate a rate. So how are we actually going to do that? Well, once again, there is a worked example which is designed to help you do the calculation. So here we go. So I'm just going to move to the relevant part. So over here, we have figure 3.6. This actually shows you the worked example where the numbers are coming from. And over here on the left, we actually have the worked example. Okay, so in the case of question 3, how are we going to do this? Well, once again, we need to start by working out what 1 millimeter on the diagram represents in terms of kilometers. So we can see that the scale bar is 5 centimeters long, and this represents 200 kilometers in distance. So first of all, we need to take that 5 centimeters and convert it into millimeters. So that's 5 times 10 gives us 50 millimeters. We know the scale bar is 200 kilometers long. We know the scale bar on the diagram is 50 millimeters long. So that represents 4 kilometers for every 1 millimeter on the diagram. Okay, so we have our conversion factor now. So now we need to calculate the distance between our 2 points. So in this case, it's C1 and C3. Okay, so we take our ruler, we measure the distance, and the distance is 1.4 centimeters. So once again, we need to begin by converting that to millimeters. So 1.4 multiplied by 10, 14. And then we need to take our 14 millimeters and multiply it by our conversion factor. So 14 multiplied by 4 gives us 56 kilometers. So the distance between C3 and C1 is 56 kilometers. Now remember, this is kilometers. The rate is in centimeters, so we need to take that distance and convert it into centimeters. So that's simply going to be 56 kilometers multiplied by 1,000 gives us 56,000 meters. And then 56,000 meters multiplied by 100 gives us 5.6 million centimeters. All right, so we now have our distance in centimeters. So now we need to also work out our difference in years. So as you can see, we have the ages for our 2 locations. In this case, the age of location C3 is 0.3 million years and C1 is 2.5 million years. Okay, so we have a situation where 2.5 million years minus 0.3 million years gives us a difference of 2.2 million years. So the difference in age between location C3 and location C1 is 2.2 million years. So now we need to convert that into years. So we're simply going to take our 2.2 million years, multiply it by a million, and that's going to give us our difference in age in years. So now we have our 2 numbers that we need. We have our distance in centimeters, our difference in age in years. So we're going to take our distance, divide it by the difference in age, and that's going to give us our rate. So in this theoretical example, it is 2.55 centimeters per year. So that was the rate of plate motion between C3 and C1. Now I'm just going to come back up here to figure 3.5 and we're going to return to the table. So you would fill this information out in this portion of the table right here. So that's between C3 and C1. So then we're going to have distance between C1 and height. So that's going to be from C1 here to this location here. Okay. And so you're going to measure the distance from here to here, convert it into centimeters, work out the difference in age, convert that into years, and then use those values to calculate your rate between those 2 locations. And you're going to do that for each of the locations on the diagram. And so just to make sure there's no misunderstandings, you can see the stations for each part are listed in the left-hand column of the table. Okay. So next we come on to question 4. So based on your answers to question 3, has the rate of motion for the North American plate remained constant? So when you look at your table of answers for question 3, is the rate value that you calculate between each of these stations the same? If it is the same, well, yes, the rate of motion has remained constant. However, if the number is different, then the rate of motion has not remained constant. So that will mean there will have been periods of time when the rate of motion will be faster and periods of time where the rate of motion will be smaller. In terms of the range, you also need to give that. So obviously your range is going to be what was the slowest rate, what was the fastest rate. So that's your range, slowest and fastest values. Okay, so now we're going to move on to part 3 of the lab exercise, and this is going to deal with convergent plate boundaries and how we use earthquakes to investigate the processes that are taking place at them. So the existence of convergent plate boundaries was first proposed by Harry Hess in 1962. So as part of the data set that he collected from multiple ocean basins, he noted that in some instances the margins of the ocean basins were marked out by the presence of a very deep trench. And he noticed this in several areas, including off the west coast of South America, the Aleutian Islands that separate Alaska from Russia, off the eastern and southern coasts of Japan, and off the eastern coast of the Philippines. So when Hess went and proposed the idea that these regions of elevated terrain within the ocean basins represented the location of new crust being made, he obviously had to come up with a mechanism that would allow old crust to be destroyed. And so Hess proposed that these deep trenches that he observed actually represented the location at which point the old oceanic crust was being destroyed. Now, one of the things that Hess was uncertain about is how it was being destroyed. So we now know that the process of subduction will take that old oceanic crust and it will push it down into the mantle, and eventually it will be destroyed and it will be incorporated into the mantle. Now, over time, we have realized that there are actually 3 different varieties of convergent plate boundary. So there's the one that we typically think of, the ocean-continent convergent plate boundary, and this is represented by the west coast of South America, where you have the Nazca plate, which is oceanic crust, subducting underneath the more buoyant continental crust of the South American plate. We also have ocean-ocean convergent plate boundaries. This is where 2 pieces of oceanic crust meet and one is subducted under the other. A classic example of this would be somewhere like the Aleutian Islands or the Philippines Trench. In these instances, what you're seeing is the result of one of the pieces of oceanic crust typically being slightly more buoyant than the other. And this is often either a reflection of the age of the crust, so as oceanic crust gets older, it tends to get heavier. That's due to the fact that it cools down and so it becomes, less buoyant, but also it starts to build up a thicker layer of sediment on top. So typically when you have old oceanic crust meet younger oceanic crust, it'll be the older oceanic crust that will get subducted. There are also instances where the oceanic crust, which is being subducted under, so the piece that's not being subducted, will actually be attached to a piece of continental crust, and that continental crust will give it added buoyancy. So a good example of that would be the oceanic crust around the Aleutian Trench, which is connected to the North American plate. So you have the continental crust of the North American plate connected to this piece of oceanic crust. So when the oceanic crust of the Pacific plate meets it, it's the Pacific plate that subducts down into the mantle. Now, the final type of convergent plate boundary is the continent-continent convergent plate boundary. This is represented by areas like the Himalayas, and in this instance there's no subduction, but what has happened is subduction has destroyed the oceanic crust between these 2 pieces of continental crust, and in the process of that oceanic crust being destroyed, it will eventually lead to the collision of these 2 pieces of continental crust, leading to the formation of a mountain range. Okay, so what we're going to do is we are going to be looking at data from the Aleutian Islands. So we're going to be looking at the Aleutian Trench. So here we go. So here's the data in figure 3.7. This actually is real world data from the USGS. And so each one of these circles represents a location of an earthquake that has occurred along the Aleutian Trench. And you can actually see here is the Aleutian Trench running right along here. You have the Pacific plate to the south, and the North American plate to the north. So when you look at each of these earthquakes, what information do we have? So we have a distance in kilometers and we have a depth in kilometers. So the distance is measured from the trench itself. If you are measuring on this side of the trench to the south, the value you get will be positive. If you are measuring on the northern side of the trench, so in this area, the value will be negative. So if we drop down to figure 3.8, you will see that right here. So this diagram represents a cross-section, a slice through the Aleutian Trench area. So the Aleutian Trench itself is marked out as 0. To the southeast of it, to the south and southeast, you get positive distance values, and to the north and northwest, you get negative distance values. Okay, so when you look at this table of data, if you see a positive value like 21 here, you know that the earthquake must be one of these to the south and southeast of the trench, whereas if you see a negative value like that one there, you know that it must be one of these earthquakes to the north or northwest of the trench. Now, why do we get earthquakes occurring during subduction? Well, there's a few reasons. Shallower earthquakes are often the result of these two pieces of crust simply rubbing against each other, because it's not a smooth conveyor belt-like process. The movement that occurs at a subduction zone between the two pieces of crust is stepped. It occurs in spurts of activity. And so you're going to see the crust will slip past each other, creating an earthquake, and then it will lock in place, and then it will keep locked in place until friction is overcome, at which point it will slip again, and so on. And this will lead to the formation of shallower earthquakes. Now, when we look at deeper earthquakes, these tend to be associated with the subducting slab entering the mantle. And so there's a couple of causes. So the first thing we need to remember is that the mantle we're talking about here is solid or semi-solid. So as the piece of oceanic crust is pushed down into it, the mantle is going to resist. It's not going to naturally want to make way for the piece of oceanic crust. And so that means that there, once again, is a lot of friction as that oceanic crust is pushed down into the mantle, and that will lead to earthquakes occurring. There is also another cause of earthquakes in the subducting slab, and this is due to changes in the mineralogy of the subducting oceanic crust. So as the oceanic crust heads deeper into the mantle, you're going to see increasing pressures and temperatures, and this means that some of the minerals in your oceanic crust are going to become unstable. And so, they're going to have to change into new minerals which are stable at these higher pressures and temperatures. So what's going to happen is when you get these changes occurring, you are going to see, in some instances, a change in volume. So, for instance, mineral A might become unstable and it will turn into mineral B. Mineral B will have a smaller volume than mineral A. And so that will actually result, as the change occurs, in the entire piece of crust actually becoming slightly smaller, because mineral A is being replaced by the volumetrically smaller mineral B. And so this change in volume can actually cause the oceanic crust to begin to split, and this can form earthquakes. But you can also get a situation where the oceanic crust essentially begins to become a bit thinner, and that actually then allows the mantle rocks to essentially fill the space that's created, and this once again can lead to earthquakes being produced. So there are lots of different reasons why earthquakes are produced, and they will be produced at a range of different depths depending on what's happening. Shallower earthquakes will be the result of the two pieces of crust simply rubbing against each other, whereas deeper earthquakes will be the result of the subducting piece of oceanic crust interacting with the mantle. Now, if we look at these earthquakes from our data set, we can also see that there is a big range in depth. So we have some earthquakes that are very, very shallow, like 1 kilometer in depth, and we have some earthquakes that are very, very deep, like 213 kilometers in depth. So there's quite a big range there. So what are we going to do in part 3? So for question 1, we are going to look at the data in table 3.2, which is the table we were just looking at, and we are going to plot the location and depth of the 38 earthquakes on figure 3.8. Okay, so here we go. Let's come back down to our table of data. You can see that there are 40 earthquakes total, However, 2 of them are highlighted, one in blue, one in red. These points have already been plotted, so there are going to be 38 other earthquakes that you are going to plot, and they are going to be plotted on figure 3.8, which is right here. And it's a relatively straightforward process. For each earthquake, you're going to get a distance measurement. Remember, some values will be positive, some values will be negative. So let's, for instance, say that the value you get is minus 50 kilometers, so you know it's going to be right here. And then you're going to get a depth measurement, let's say 50 kilometers, so you know your earthquake occurred right here. Okay, and then you're going to make a point right there simply by drawing. You can do it by drawing a circle in either Adobe Acrobat or in Word, or if you want to, for a slightly easier drawing experience using Microsoft products, you can copy and paste this diagram into PowerPoint, and that's typically a little bit easier. So for question 2, once you've plotted all of these points, we are now going to begin to analyze the data. So for question 2, using the thickness of the average oceanic lithosphere, which is marked out here as this shaded green area. So this is the average thickness of oceanic lithosphere, which is about 70 kilometers on average. So what you're going to do is you are going to use the earthquake data that you plotted, and you're going to draw the outline of the Pacific and North American plates. So remember, one of these plates is going to be subducting underneath the other. So when you look at the data set, you are probably going to notice a distinct pattern in the earthquakes that's going to give you an idea of the path which is being taken by the subducting oceanic crust. And so what you can do then is you can then use the position of these earthquakes to approximately mark out the location of the subducting oceanic crust as it goes down into the mantle. So for question 3, you are going to label the Pacific and North American plates on figure 3.8. So once you've drawn the location of the 2 pieces of crust, so the 2 plates, you will label the North American plate as North American plate, and you'll label the Pacific plate as the Pacific plate. Relatively straightforward. So for question 4, based on your plot of the earthquake data, what is the dip angle of the subducting oceanic crust? Subducting spelt incorrectly there, please ignore that. So what's going to happen is when you plot the data, it's obviously going to show a piece of crust going down into the mantle at an angle. It could be coming down in this direction, it could be coming down in this direction, it could be dropping very, very steeply, or it could be very, very shallow. All right, you won't know until you plot the data. But what you can do once you do have the data plot, and once you've drawn the location of the subducting slab, you can then take a protractor and you can give an approximate angle at which it is entering the mantle. Then we have question 5. So then using the data that we plotted on figure 3.8 and the plan view of the Aleutian Trench in figure 3.7. So this is the plan view right here where you can see all of the earthquake locations. What is the general direction of plate movement for the Pacific plate in this region? Okay, so the general direction of movement is going to be the direction in which the Pacific plate is subducting. Okay, so if it's subducting to the north, the plate motion is going to the north. If it's subducting to the south, the plate motion is to the south. Okay, so once you've plotted everything on here, that's going to allow you to answer all the other questions. Now, some people may feel a little bit uncomfortable about how they're going to collect the information to answer these questions, so you have a couple of options when it comes to taking measurements for this lab exercise. The first way you can do it is the more straightforward method. You can simply print out the lab and use a ruler to take the measurements. However, I do appreciate that not everybody will have access to a printer and so won't be able to do that. So for those students who will be using their computer to complete these lab assignments and take measurements, you should please go to the class D2L page. You should go into the content section and you should find the folder called Using Your Computer to Complete Lab Assignments. And in this folder, you're going to find a video and it's going to explain how you can take measurements using Microsoft programs and how you can also take measurements using Adobe Acrobat. And hopefully that will give you the information that you need in order to take your measurements to answer the questions. If you hit any problems, please don't hesitate to email me. I will get back to you as soon as I can. Anyway, thank you for watching this video and have a good day.